Good morning, friends. Today we'll be discussing about Raman spectroscopy under the heading molecular spectroscopy. Today we'll be discussing about Raman spectroscopy, about the introduction, then what is Raman effect, what are Stokes and anti-Stokes lines, then what are the advantages of Raman spectroscopy over infrared spectroscopy, and what is meant by polarizability. So these are the things we should be discussing today. And according to e-content preparation, today is a discussion on session 61. It's a discussion about section 61 of Raman spectroscopy. So in the previous lectures, we discussed about what is molecular spectroscopy, what are the types of spectra we have. So we learned that there are two types of spectra, namely absorption and emission spectra. The other way of classification is it atomic spectra and molecular spectra. And we learned that in absorption spectroscopy, the transmitted light is analyzed and the spectrum obtained is called the absorption spectrum. And in the case of emission spectra, the emitted light, the light emitted by or the radiation emitted by the substance is analyzed and recorded. Such spectrum obtained is called emission spectrum. And in contrast to this absorption and emission spectrum, Raman spectroscopy deals with the study of scattered light. So it is a different type of spectroscopic technique. In Raman spectroscopy, the scattered light is analyzed and the spectrum obtained is called Raman spectrum. And whenever radiation falls or passes through a substance, a fraction of the light is reflected, a fraction of the light is absorbed, a fraction of light is scattered, remainder is transmitted. And the scattering of radiation or light by a substance takes place in all the directions, but the scattered light is analyzed at right angles to the passage of incident light. So, in Raman spectroscopy, as I said, it is the scattered light which is analyzed, and the spectrum obtained is due to analysis or study of scattered light, and the spectrum is called Raman spectrum. So, what is this Raman spectroscopy? Raman spectroscopy is based on Raman effect, which was published in the year 1928, and this Raman effect fetched Sir C.V. Raman Nobel Prize in 1930. So this Raman spectroscopy is based on Raman effect. So C.V. Raman, he found that in the scattered light, the frequencies are different from that of incident light. In the sense, whenever a substance is irradiated with light, the scattered radiations will have frequencies other than the frequency of incident radiation. This is called Raman effect. So Raman effect is the phenomena in which the scattered radiations from a substance will have frequencies other than that of incident frequencies. So when we say that the scattered radiations will have frequencies different from that of incident frequency, it means that the scattered radiations may have higher or lower frequencies than that of incident radiation. Right. So the difference in the frequency, which is called as Raman frequency. So the difference in the frequency of scattered radiation from that of incident radiation is called Raman frequency, denoted by delta nu, where nu stands for frequency. So this delta nu is equal to mu I minus mu s, where mu I stands for frequency of incident radiation and mu s stands for frequency of scattered radiation. So, the difference in the frequency of scattered light from that of incident light is called Raman frequency denoted by delta nu. So, which is given by the expression delta nu is equal to mu I minus mu s, where mu s stands for frequency of incident radiation and mu s stands for frequency of scattered radiation. So, if frequency of scattered radiation is less than that of frequency of incident radiation, then delta nu is greater than 0, and the spectral lines so obtained are called as Stokes lines. So, if the frequency of scattered radiation is less than that of incident radiation, Raman frequency delta nu will be a positive quantity that is greater than 0, and the spectral lines for which delta nu is greater than 0 are called as Stokes lines. And if frequency of scattered radiation is more than that of incident radiation, delta nu will be less than 0. So, the spectral lines for which delta nu is less than 0 are called as anti-Stokes lines. So, this is Raman effect. So, Raman for the first time discovered that the scattered radiations from a substance will have frequencies different from that of incident radiation, and the difference in frequencies of scattered radiation and incident radiation is called Raman frequency, and this Raman frequency delta nu could be greater than 0 or less than 0. And if delta nu is greater than 0, it is called Stokes lines. And if delta nu is less than 0, the spectral lines are called as anti-Stokes lines. And apart from this, the scattered radiation will also have the frequency equal to that of incident radiation. So, there is another fraction of scattered light whose frequency is equal to the frequency of frequency of incident radiation. So, mu I is equal to mu s means where the frequency of scattered radiation is equal to frequency of incident radiation. Such scattering is called as analogous scattering. And when we are analyzing the scattered light, we should know that only very small fraction of the radiation is scattered by the sun. Approximately 10 to the power minus 7% of the incident radiation is only scattered. Therefore, Raman spectral lines, when compared to other spectra like infrared spectra or invisible spectra, will have weaker intense lines. Right. So, this is a Raman effect, which fetched Sir C.V. Raman the Nobel Prize in 1930. So, now let us see what is the reason for difference in frequency of scattered radiation from that of incident radiation. And this can be schematically represented. So, these are vibrational energy levels. And at room temperature, most of the molecules will be in the vibrational ground state. And when radiation falls on the substance, the energy from the radiation is absorbed by the molecules, and they go to some higher rotational energy level or vibrations. These are called virtual energy levels. The dotted lines are called as virtual energy levels. Why they are called virtual energy levels? Because these energy levels could be either higher rotational energy levels or higher vibrational energy levels. So, when the molecules in the ground state absorb the energy from the radiation and go to some higher rotational or vibrational states, which are short-lived. So, from that excited higher energy state, the molecules come back to the original ground state. In such case, the frequency of incident radiation would be equal to frequency of scattered radiation. So this type of excitation, de-excitation leads to Raman scattering. So whenever the process like this, when the initial state, final state, and the initial state are the same. When the molecule goes from V is equal to 0 state to any higher energy level and comes back to the same state after emptying out the energy, that type of scattering leads to Rayleigh scattering. On the other hand, when the molecules take transition from vibrational ground state to any higher rotational or vibrational energy level, then if the molecules come back not to the ground state but some other vibrational state, in such case, frequency of incident radiation will be greater than frequency of scattered radiation. Because some of the energy absorbed by the molecules is retained within the molecule, therefore only fraction of the energy absorbed is given out. So scattered, therefore scattered radiation will have a lower energy than incident radiation, or in other words, in such case, frequency of scattered radiation will be less than the frequency of incident radiation, because we know E is equal to h nu. So energy of the photon is directly proportional to frequency. So energy of the scattered radiation will be less than the energy of incident radiation, because a fraction of the energy is retained by the molecules while coming back to ground state. Hence, the frequency of scattered radiation will be less than the frequency of incident radiation. Such conditions will give rise to Stokes lines. And at room temperature, most of the molecules will be in the V is equal to 0 state or ground state. But a small fraction of molecules may be present in higher energy, higher vibration state. V is equal to 1 also, because energy gap between the vibration levels is very small. So major fraction of the molecules at room temperature will be in the V is equal to 0 state. Small fraction of the molecules would be present in the V is equal to 1 state. So when the molecules present in the V is equal to 1 state take up energy from the incident radiation, move to a higher energy state, which could be a rotational or vibration energy state, then it comes back to the V is equal to 0 state as ground state. Look at the molecule initially was present in V is equal to 0 state, V is equal to 1 state. After absorption energy from the radiation, it has gone to, it is excited to higher energy state. Then it has returned from higher energy state to V is equal to 0 state, but not V is equal to 1 state. In the sense, some of the energy of the molecule is given to the scattered radiation. Therefore, in such type of transitions, energy of scattered radiation will be more than energy of the incident radiation. Or in other words, frequency of incident radiation will be less than the frequency of scattered radiation, because some amount of energy from the molecule is given to the radiation. Therefore, scattered photon will have a higher frequency or higher energy than that of incident radiation. Therefore, such type of transitions will give us spectral lines which are called as anti-Stokes lines. So this is how we can explain the difference in the frequency of scattered radiation from that of incident radiation with the help of the diagrams. So once we have understood the reason for the difference in frequencies of scattered radiation from that of incident radiation, let us now see what would be the difference in the Raman frequencies from that of infrared frequencies, because Raman spectroscopy is considered as complementary to the infrared spectroscopy. Why is it so? So, the frequency of Raman spectral lines are almost close to the frequencies of IR spectral lines. In the sense, the new frequency value of spectral lines in Raman spectrum are almost very close within the experimental errors to that of IR frequencies, which means that the information that we get from Raman spectroscopy is similar to that of information we obtain from infrared spectroscopy. If that is the case, if the information that we obtain from Raman spectroscopy is same as that of infrared spectroscopy, then why is necessary to study Raman spectroscopy? So there are few advantages of Raman spectroscopy. So what are those advantages of Raman spectroscopy over infrared spectroscopy? We learned that the difference in frequencies of incident and scattered radiation is called Raman frequency, which is denoted by delta mu, which is given by ui minus us. So this Raman frequency delta mu is independent of incident frequency. In the sense, in infrared spectroscopy we use only infrared radiation. In microwave spectroscopy we use only microwave radiation. In the case of UV vision spectroscopy or electron spectroscopy, we use only UV visible radiation. On the contrary, in Raman spectroscopy, we can use either UV visible light or a laser beam or even X-ray beam of suitable frequencies. So the main advantage of Raman spectroscopy is that we can use either lasers or X-rays or ultraviolet or visible radiation for excitation of the molecules. Whereas other spectroscopic techniques need only particular fraction of electromagnetic radiation. That's one advantage. Second advantage is that Raman spectroscopy can be studied for gases, liquids as well as solids. But in the case of infrared spectroscopy, we require essentially the sample in solid state. So second advantage is that Raman spectroscopy can be used to study the gases, liquids as well as solids. Third advantage is that even non-polar molecules like oxygen, nitrogen, hydrogen, etc., which cannot be studied either by microwave spectroscopy or infrared spectroscopy, can be studied by Raman spectroscopy. Please look at the other advantage, that is non-polar molecules like O2, N2, H2, CO2, which cannot be studied by microwave or infrared spectroscopy, can be studied by Raman spectroscopy. So these are certain advantages of Raman spectroscopy over infrared spectroscopy, because though the information that we obtain from Raman spectroscopy is similar to that of infrared spectroscopy, because of these advantages, Raman spectroscopy has got an edge over infrared spectroscopy. So we learn that non-polar molecules which do not have permanent dipole moment, like O2, N2, S2, CO2, etc., can be conveniently studied by Raman spectroscopy. Now, what is the condition for a molecule to be Raman active? As we learned in the case of microwave spectroscopy, if a molecule is to be studied by microwave spectroscopy, the molecule should possess a permanent dipole moment. That's why CO2, N2, O2, S2, etc. cannot be studied by microwave spectroscopy. And if a molecule is to be analyzed or studied by infrared spectroscopy, then the molecule should undergo change in dipole moment during its vibration. That is the condition for higher activity, change in dipole moment during vibration. Similarly, if a molecule is to be studied by Raman spectroscopy, or in other words, if the molecule is to be Raman active, the condition is that there should be change in polarizability of the molecule. So the condition for Raman activity of a molecule is that there should be change in polarizability of the molecule during rotation or vibrational motion. So if there is change in dipole moment during rotational motion, it gives rise to rotational Raman spectrum. If there is change in dipole moment during vibration, there is change in polarizability during vibration, it gives rise to vibrational Raman spectrum. So the condition for Raman activity of the molecule is that there should be change in polarizability of the molecule during the rotation or vibration in the presence of an electric field, like that of electromagnetic radiation. So electromagnetic radiation, as the name itself indicates, is associated with electric and magnetic fields. So whenever a sample or substance is irradiated with radiation, the electric field associated with this electromagnetic radiation induces dipole moment in the molecule. In the sense, a non-polar molecule or a molecule which does not possess dipole moment will undergo polarization under the influence of electric field associated with electromagnetic radiation. So that is called as a polarization. So a non-polar molecule is polarized in the presence of an electric field, and that process of separation of charges is called polarization. So what is polarizability then? The ease with which a molecule can be polarized is called polarizability of the molecule. So the condition for a molecule to be Raman active is that there should be change in polarizability or induced dipole moment during rotation or vibration. Only when such change in polarizability takes place during rotation or vibration, then only it gives rise to Raman spectrum. So, we have learned that polarizability is nothing but the ease with which a molecule can be polarized in an electric field is called polarizability. So, what is polarization? Separation of charges. As you have seen in the case of HCl, which is a polar covalent molecule, and in the case of nitrogen, which is a pure covalent molecule. So, either of nitrogen atoms in N2 molecule does not possess any charge. Therefore, this is a non-polar molecule. But in the case of HCl, which is also a covalent molecule like nitrogen, hydrogen carries a partial positive charge and fluorine carries a partial negative charge. Therefore, there is a charge separation. That is nothing but polarity is present in the molecule leading to dipole. So charge separation is called polarization. So whenever a substance is irradiated with electromagnetic radiation, under the influence of electric field associated with electromagnetic radiation, the molecule gets polarized. So for example, if you consider a carbon dioxide molecule, which is a non-polar molecule. It's a linear molecule. Though there are two dipoles due to CO bonds, and since they are equal in magnitude and opposite direction, net dipole moment is 0. And when that CO molecule, carbon dioxide molecule, if you represent like this, so when these carbon dioxide molecule undergoes symmetric stretch, in the sense CO bonds move in opposite direction. So this type of vibration is called symmetric stretch, where both CO bonds stretch in opposite directions. Because of this symmetric stretch, there is a change in dipole moment of the molecule. There is a change in bond length. Therefore, when it is stretched to this extent on both the sides, there is a change in polarizability. So, this symmetric stretch of CO2 is Raman active. Hence, as I said, carbon dioxide molecule which cannot be studied by either microwave spectroscopy can be studied by Raman spectroscopy because symmetric stretch of CO2 is IR inactive, it is microwave inactive, but symmetric stretch of CO2 is Raman active. Therefore, it is possible to study the vibration modes of carbon dioxide by Raman spectroscopy. And when we consider asymmetric stretch, what is asymmetric stretch? One CO bond gets lengthened, the other CO bond gets shortened. In the sense, both the CO bonds are moving in the same direction. So this is called asymmetric stretch. Look here, this is the symmetric stretch, and this is asymmetric stretch of carbon dioxide. Symmetric stretch leads to change in polarizability. Therefore, it's Raman active. This is Raman active stretch. Whereas when you look at asymmetric stretch, in one case bond length is increasing, this bond length is increasing, this bond length is decreasing. Change in polarizability during this stage is compensated by the shortening change in polarizability in the opposite direction due to shortening of the CO bond. Therefore, this asymmetric stretch is Raman inactive. Whereas asymmetric stretch of CO2 is IR active. Whereas asymmetric stretch of CO2 is Raman inactive. Similarly, symmetric stretch of CO2 is Raman active, but same symmetric stretch of CO2 is IR inactive. Because symmetric stretch does not lead to change in dipole moment. Therefore, symmetric stretch of CO2 is IR inactive, but it is Raman active. And asymmetric stretch of CO2 is IR active, but it's Raman inactive. So, this difference tells us that Raman spectroscopy is complementary to infrared spectroscopy. So, let us stop here and let us see in the next session the rotational Raman spectroscopy and vibrational Raman spectroscopy. Thank you.